Welcome back, everyone. I'll be chairing the second session of the day, and I would like to welcome Bruce to present his work about CDW order and fluctuations in the superconducting Kagome metal.
Great.
Thank you.
So thanks very much, Moishe. Yeah, so, well, first of all, I'd like to thank Yasir and Ronny for inviting me to this actually wonderful institute. Very pleased to be back in India. So thank you for your very fine hospitality. I'm going to be telling you about a series of X-ray scattering experiments, which, as I'll describe, are actually low-resolution X-ray scattering experiments. And people don't usually brag about doing low-resolution anything, right? Because everybody likes to do high-resolution measurements and whatnot. But I'm going to show you low-resolution measurements, and I'm going to make the case that you'll see something different and complementary to what you see in actually what's more traditional high-resolution X-ray diffraction. So that's what I'm going to focus on. And this was a study actually which was initiated by a coffee time conversation with Claudia Feltzer at a CFAR meeting, and CFAR is an organization I belong to in Canada that sponsors kind of small meetings like this, actually. And her group, she's a director at the Max Planck Institute in Stuttgart, and so her group does a lot of material synthesis and low temperature characterization. Actually, is very well known, of course. And at the time, they had just synthesized this family of the 135 materials that we've heard so much about already. So these are my collaborators. This is Chong Chen, who is the postdoc in my group, a very good postdoc, who did all of the X-ray scattering work and all of the magnetic susceptibility. And then Claudia Feltzer's group actually grew the materials and did the heat capacity measurements. So that's the collaboration. And of course, you know, the talk here wouldn't be complete without showing this diagram, which you know, I wish I'd counted, you know, started counting how many speakers had shown this, and you know, it's a lot. So I mean, you know, the interest in these type of, you know, Kagome metals that you get even at this very simple level of near neighbor hopping through the Kagome lattice. So this has been discussed, you know, many times over. You have these two different Van Hove singularities and the Dirac cone and a flat band. Okay, and you know, so actually, you know, even though this sort of physics is very familiar, I think, to you, it actually isn't that familiar to me because much of the work that I've done is in neutron and X-ray scattering, and much of it has actually focused on magnetism in insulators. And so that's my venue, or that's the way I sort of entered this field of Kagome materials, and this just so happens to be a Kagome metal. And so I think it's very well known that you know, because it's a network of corner sharing triangles, that in the presence of antiferromagnetism, you know, it strongly supports you know, frustrated states. And if you do have localized moments, you know, decorating these sorts of lattices, actually, you know, one of the reasons why the Kagome lattice is so famous, actually, in magnetism is that because you know, with a very simple argument about the energy per spin associated with a classical Néel ground state and a quantum either valence bond state, if you like, or a state made up of singlet pairings of the spin-half degrees of freedom, you know, this is one of the rare cases where the quantum ground state is lower than the classical ground state. Okay, and it's lower for two reasons. You know, one is that the energy per spin classically depends on the number of near neighbors. It depends on the coordination number, and the coordination number is low for the Kagome system. It's only 4. And in addition, the classical spin configurations, if you've got continuous spins, they don't fully anti-align, right? So they're canted at 120 degrees to each other. So you don't get the full, you know, minus s squared type term that you would get if you were in a non-frustrated geometry. Anyway, the net result is that this is a lower energy than this is. And so that spurred a lot of interest in quantum antiferromagnets on a Kagome lattice, and there's been there's a huge literature associated with that. And anyway, so that's what I'm more familiar with. And there is actually analogy to the magnetic excitations, on these sorts of lattices, and the flat bands, at least, that you see in the simple band structure that you expect from just a simple near neighbor hopping type model for the electronic system. And that actually comes about in the classical models, right? It doesn't come about in the quantum version, so it doesn't appear in quantum antiferromagnetic materials with Kagome lattices like Herbert Smithite, which was discussed in one of the last lectures. And it doesn't appear there because the elementary excitations are not spin waves, they're spin-ons, right? So you get a continuum of excitations. There's no sharp excitations in that case. But classically, there are. Classically, you do get this sort of a Nail state. And you've got actually three, because there's three magnetic moments per unit cell, there's three spin wave modes in the Brillouin zone, one of which is essentially a flat mode, okay? And that flat mode is sometimes referred to as a weather vane mode, and it's where you get these correlated rotations of the spins around a hexagon, okay? So it's if you remember Ricardo Komen's discussion about the localized nature of the Wannier orbitals, electronically, this is actually somewhat similar. Anyway, when I first got involved in this, that's where I was coming from. And so what I was expecting the field to be like is to be, illustrated by, this sort of cartoon over here, which I took out of one of the recent review articles, which it's supposed to represent, some sort of spin liquid, frustrated spin liquid state with local moments on the Kagome vertices. In the presence of itinerant carriers. And this is the sort of thing that I was expecting to find. But actually, that's not, of course, what happens at all in these, at least in these 135 Kagome metals, because there are no local moments, right, to begin with, or at least there's nothing obvious. I know there's been a lot of discussion about time reversal symmetry breaking, but there's certainly no large moments that are present, say, on the vanadium site. Nonetheless, this is the sort of thing that I was expecting. Anyway, so we all know that in 2019, this family of new Kagome metals, they weren't yet identified as superconductors, was discovered. This is the discovery paper here by Ortiz et al. In Stephen Wilson's group, and again, this picture has been shown here, and you end up with this stacking of essentially vanadium ions that decorate a Kagome lattice, and they're stacked on top of each other. So we've had a lot of discussion on this, and then this data has also been shown multiple times over. And one of the very exciting things, which was discussed, well, at least published a year later, was that in cesium, vanadium, and timidite, and actually in the other two members as well, they have superconducting ground states, which were initially identified. This is the heat capacity data here with a TC that's around 2.5 Kelvin. And actually, when I saw this data initially, I thought that this was the first superconducting ground state in a Kagome material. And actually, the literature is a little vague on how many other Kagome materials there are, metallic Kagome materials that have superconducting ground state. But this is a diagram that was taken out of this review paper from 2 years ago, which purports to identify all the Kagome type superconductors and plots their TC versus the London penetration depth. And this new family of superconductors resides over here. It has a relationship that's similar to the cuprates, but a little bit over to the side. But the thing to note is that there's many entries here, and I'm not really sure how many of them are really equivalent to the stacking of Kagome layers this, either simple or alternating stacking of Kagome layers. That's certainly true for these. Actually, cerium ruthenate, there's only two materials which are called out on this diagram, cerium ruthenate being one of them, but cerium ruthenate is actually a Lavis phase cubic structure. So this is, very similar to one of the, the pyrochlore metals that Ricardo Kohlmann was talking about. And, so there are Kagome planes there, but they're not stacked on top of each other. They form, these three-dimensional interpenetrating, non-coplanar lattices, right? So it is cubic. It's really quite different, although there are Kagome planes. And this one here is a stacking of Kagome layers, and they're almost stacked right on top of each other, but there's small differences. Anyway, if anybody knows what all these other points represents, I'd be interested in finding out what they are, because it's not completely clear from this paper. Anyway, and of course they also had this very interesting charge density wave anomaly that was identified in the first experiments in susceptibility and resistivity, and at 94 Kelvin. And actually, some of the features associated, some of the physical parameters associated with this material, vary a lot or a fair bit from, sample to sample and this sort of thing. This one doesn't, right? This 94-degree anomaly is there in pretty much every sample, and it's bang on at 94 Kelvin. And that'll be important for reasons that I'll go into in just a moment. Yeah, so just looking at that in a little bit more detail, this shows, two sets of order parameters, one from the night shift for vanadium NMR, which is, really is a high resolution type measurement. So here's the data here. And you see, not a lot of structure, but a very abrupt drop at exactly 94 Kelvin, and then no night shift beyond that. And then here's one of about 5 or 6 published X-ray diffraction studies, high-resolution X-ray diffraction studies, which actually show a somewhat different order parameter. There's two different. The charge density wave corresponds to a doubling of the unit cell within the Kagome planes, and a doubling of the unit cell in the stacking direction perpendicular to it, or a quadrupling of the unit cell along the stacking direction. And actually, both of these, this is the data here, and both of these can be identified in this data. And I don't know how well you can see this or appreciate it, but this is a reciprocal space map of H on the x-axis versus L on the y-axis, and the spots that you see here at H equals a half, in the low temperature case, they're separated by a half of reciprocal lattice vector, and at high temperatures they're separated by a quarter of a reciprocal lattice vector. So that's what identifies them. Anyway, the only reason I wanted to call out this particular high-resolution X-ray scattering measurement instead of any of the other 4 or 5 that have been published that are similar to this, but they're not the same as this. And Stephen Wilson discussed this in his talk. He talked about the variation that you can get in basically the stacking periodicity that's observed in these sorts of experiments. That can be, well, I wouldn't say controlled is too strong a word, but that can be altered by quench rate and exactly how well you equilibrate the sample, among other reasons. But the reason I'm showing this is that it was performed by some of our collaborators on the same samples that we performed our measurements on, right? So that's why I'm showing it. And once again, it shows this very abrupt and very discontinuous phase transition at about 94 Kelvin, okay? Right. So as was discussed, I mean, this won't be relevant for my talk, but as was discussed by Stephen Wilson and others, the nature of the charge density state, charge density wave state is that it goes from what's essentially a perfect Kagome lattice at high temperatures to a distortion which has a period 2 doubling in the AB plane. And then, that distortion can either be the Star of David type of distortion or this trihexagon type of distortion. And then you can stack these layers on top of each other in different ways. And I think actually the very first talk in our workshop, discussed the possible ways that this could be done. They could be stacked on top of each other. They could be stacked in an alternating way. You could stack, Star David with trihexagon and so forth. Anyway, you can sort of imagine that all of that sort of crystallography is actually not that easy to do, given the complexity of the unit cell. And the low resolution X-ray scattering that I'm going to be describing is inappropriate to address this, so we don't address it, right? And you'll see I won't really mention it again. But I just wanted to mention it here. And what we know, or what we believe in cesium, vanadium, antimonide, is that there's an alternation actually of these two layers as you go along the C direction, and you can get either a period 2 or a period 4 structure, right, by doing so. Right. So anyway, so here we are studying actually the same samples that were studied before. Not exactly the same samples, but samples taken from the same growth. And this is our characterization of these materials. So this is the diamagnetic susceptibility. Well, actually, sorry, yes, this here is the diamagnetic susceptibility associated with the superconducting transition, and this is the heat capacity anomaly associated with the superconducting transition. It's at a little bit of a higher temperature than it was for the initial samples. It's about 2.9 Kelvin now instead of about 2.5. The bulk susceptibility measurements, though, look essentially identical to the original measurements published by Ortiz et al. And that is that at high temperatures, you got a very Pauli-like susceptibility, and then there's almost a step function at 94 Kelvin, and that's true whether the magnetic field is in the Kagome planes or perpendicular to the Kagome planes. So as I said, this sort of feature is completely reproducible from sample to sample and so forth, right? Very all of this sort of evidence shows an anomaly only at 94 Kelvin. And so, people, I think, largely believe that, that is where the charge density wave begins. Actually, what I'm going to tell you is that that's not the full story. Okay. Anyway, so I've been mentioning that we do these low-resolution X-ray scattering measurements. These are sort of the way to think of them, or the way I think of them, are they're neutron scattering experiments if you did them like a neutron scattering experiment. Okay. So. So the main difference is that the X-ray source that we use is a so-called rotating anode, and it's an incoherent source, which means that the X-rays are produced and go out, they don't quite go out in all directions, but they go out almost in all directions, okay? And that's as opposed to at a synchrotron, where you have a storage ring, an electron storage ring, and if the electrons are circulating at relativistic velocities, as they are, all the radiation gets compressed into the forward direction, and you end up with almost a coherent beam of X-rays, whose spot size is about the diameter of a human hair. Okay, so it's about something like 50 microns or something like that. Whereas we have a beam that can be actually very big. It can be almost as big as a neutron beam, actually not quite that big, but it's centimeters in size, and the power associated with the source is lower. So our beam spot size compared to most X-ray diffraction is relatively large, and what that means is that the power that's delivered to the sample is relatively small. It's about a factor of 10,000 lower than the equivalent experiment on even a not a particularly up-to-date synchrotron. And so there's two things. One is that there's essentially no beam heating. With the synchrotron-based X-ray scattering experiment, there's a lot of beam heating. In fact, it essentially precludes measurements with X-ray scattering below about 10 Kelvin. And it's very hard to do X-ray scattering measurements in equilibrium, in thermal equilibrium, because so much power is being delivered to a very small spot on the sample. Of course, it's better for metals than it is for insulators. This is a worse situation in insulators. But nonetheless, the measurements that we're doing, we have our sample with an exchange gas around it, and we can control the temperature of the sample to somewhere between 5 and 10 millikelvin. So all the measurements that I'm showing you, when I'm not listing the fluctuations in the temperature with the data, but when it says 10 Kelvin, that's 10 Kelvin, plus or minus roughly 5 millikelvin or so. And the reason we've set it up that way is because when I first set up this lab some 30 years ago, what I was interested in doing was critical phenomenon using X-rays and such, and so being able to control the temperature precisely was a big deal. Anyway, so we can do measurements to lower temperatures, and we can do measurements that are truly in equilibrium. It's low resolution, so it means that we cannot measure long correlation lengths. And this is something that the synchrotron or high resolution X-ray diffraction can do. But it means that any features that don't require high resolution, like diffuse scattering, so scattering that is not concentrated into a Bragg peak, we measure that very efficiently, okay? Much more efficiently than the high resolution measurement does. Okay, and so the net result of all that is that you can see things in low resolution scattering that you cannot see in high resolution scattering because they're too diffuse for the high resolution scattering. There's a mismatch between the resolution function and the phenomenon. Okay, so this is our low resolution X-ray scattering data from these samples of cesium, vanadium, and timidide. And I'm showing you intensity on a log scale. So if you just look at the central feature here, this is intensity on a log scale as a function of a particular scan in reciprocal space. It's actually a scan along the L direction, which is the stacking direction. And I'm going to use one of these panels from data that I showed you earlier, X-ray data that I showed you earlier. So these actually are not the same data, but I just wanted to show you what this sort of scan looks like in reciprocal space. So this is a scan. This would be in the HHL direction rather than the H direction, but we would be doing a line scan that would go through the series of peaks that you would get as a function of L, with peaks at 1/2, 0, and -1/2, right? So 1/2, 0, and -1/2. But you can see that we're not necessarily seeing very well-defined Bragg spots, as you see here. We're actually seeing a streak that goes up and down here, and that has considerable structure in it, right? It's really peaked at 0. In fact, the scattering at 0 is about 100 times stronger than the scattering that I'm going to focus on. Most of this scattering is temperature independent, below 300 Kelvin, okay? And it corresponds to some fluctuation that has a doubling of the unit cell within the Kagome plane, because it's at these 1.5, 1.5 indices in reciprocal space. So most of this scattering is temperature independent, but when you come to L equals +1/2 and -1/2, you get some more Bragg-like feature that actually is temperature dependent, and this is the signature from the charge density wave, which everybody else is seeing, although, as I'll show you, it's somewhat different. So actually what you see on either side here is just a blow up of this region over here, so it's showing you the part of the signal that is temperature dependent. Everything else is temperature independent, and if we just focus on that, and we integrate up and fit the integrated intensity of these Bragg peaks as a function of temperature, this is the order parameter that we get right here. And anyway, so you can see right away that it's not what's seen in high resolution diffraction, and it's not what's seen in NMR and such, and that we see this very linear growth of the order parameter. And the 94 Kelvin anomaly associated with the charge density wave, which, as I mentioned, is very reproducible from sample to sample, and it's reproducible in our samples, is almost the midway point on the order parameter, and it extends up to much higher temperatures, something more like 150 Kelvin. So the way we interpret this is that, at low temperatures, we're seeing the long-range order associated with the charge density wave state, but at high temperatures, we're seeing the fluctuations associated with the charge density wave state above the phase transition, and actually we can see them go up to very high temperatures, right? And so I was mentioning before that my misspent youth was doing X-ray scattering measurements on measuring critical exponents and such, and for most phase transitions in three-dimensional materials, you can see this sort of critical scattering. but it doesn't go up to twice the ordering temperature. It might go up to 10% above the ordering temperature or something like this. So this is actually very, very large, and but it's very characteristic of two-dimensional materials, right? The lower the dimensionality, the more extended the critical range tends to be. Anyway, it's very different than other people's order parameters. Okay. Yep. So on the samples that so this is reproducible from sample to sample of the samples that we've looked at, yes. But the samples that we've looked at are all from, they're all from the same batch, but they're actually from this batch. So this is the high resolution measurement on the same samples, or samples from the same batch rather. And from exactly the same samples, this is the susceptibility, which shows the anomaly at 94 Kelvin and doesn't show anything above that, right? So, but I am going to show you something that does show these fluctuation effects. That's what I'm going to show you next. Right, so this is the heat capacity measured over a very broad range of temperature. I've already shown you the heat capacity at very low temperatures, which shows the superconducting anomaly nicely. So this is actually C over T. So the integral of this would be the entropy associated with the sample. I mean, most of this is due to the lattice, it's due to phonons. But you can see that when you get up to higher temperatures, there's a very sharp anomaly associated with the 94 Kelvin transition to long-range order of the charge density wave. But if you do an appropriate analysis, which I'm going to tell you about now, which is that you try to smoothly connect the region, well below the clear sharp phase transition and well above the clear sharp phase transition. And there's more than one way to do this. We're using a technique that's referred to as the Thirring method, or a Thirring model, to account for the phonon contribution to the heat capacity. Like I said, other people do different things, but the basic idea is that you're trying to smoothly connect this region of the heat capacity with this region of the heat capacity. And then you're going to look for the difference between the actual data and, if you like, the simple lattice contribution to the heat capacity, which is actually most of the heat capacity. But if you do that subtraction, then of course you get this big peak at 94 Kelvin, but there's a foot associated with the thermodynamics above the phase transition, which goes out to about 150 Kelvin or so. And we believe that this is the entropy associated with the fluctuations which we're seeing in the low resolution X-ray scattering measurement. So we think this is quite consistent. And I'll show you in a minute that it's consistent with other examples as well. So that's not to say that everything that we measured in this low resolution X-ray scattering experiment, showed effects due to the charge density wave, which were very extensive. In fact, this is the lattice parameter, which is, it's just the C lattice parameter in the stacking direction. It shows a very nice discontinuity, which is actually pretty big. It's 0.1%. At 94 Kelvin, so it's clear that there is a very sharp phase transition here, but it's equally clear that there are fluctuations that go up to much higher temperatures. Okay, and then the last result, and I'll try to wrap up relatively quickly, is that because we don't have a high heat load in our sample, we can go down to much lower temperatures. In this case, we went down to about 1.9 Kelvin. And so that's about here on the susceptibility measurement. So the diamagnetic response is pretty much fully formed. At that temperature, we're at 2/3 of the of TC, and so I'm just showing you these entire scans over this range of temperature, and over here I'm showing you peak intensities just made, sitting at one of these positions and counting with very high statistics. And you can see that there's, our conclusion is that there's no change in the CDW at the 3% level as you go into the superconducting state, with that's essentially fully formed. So. Yeah, so I'll finish with this, if that's okay. And I just say, should I be should I be surprised by that result or happy with it or unhappy? And I didn't really know how to feel, right? But I have to put it into context of, really the only other system that I know of that has both a superconducting ground state and charge density waves, which are the cuprates. Okay, in that case, the superconductivity is, I think that's, definitely established as D-wave superconductivity. But in this case, and this is not controversial. This has been measured, many times over now. And I've taken this from a recent paper from 2021. But, so this is the Bragg intensity associated with the CDW in LSCO at 3 different dopings. And you can see it's very clear that you get a growth in the order parameter until you get to the superconducting transition. And then for 3 different superconducting transitions, the order parameter either plateaus or decreases by a substantial amount. So it's very clear that the CDW is anti-correlated with D-wave superconductivity in the cuprates. And if the only information that I've got to go on in these systems is are things like how do the CDW and the superconducting transition behave as you perturb the system. And here, this is data that Stephen Wilson showed. It's his data, in which you're substituting in tin for antimonide. So this is quite a big perturbation. You're actually changing the doping. But nonetheless, what you see is that the CDW goes down and the superconductivity goes up. Here's something that might be more easy to interpret because it's just hydrostatic pressure. Not just hydrostatic pressure, but it's hydrostatic pressure. And again, the CDW goes up and the superconductivity goes the superconductivity goes up and the CDW goes down. So this would also, if you're going to interpret it at all, what you would say is that they compete with each other. But in our case, our measurement, which is here, there's no obvious competition between the two. Okay? And with that, I will, I've sort of run out of time. I was going to show you an example where, we also, another example where we observe very extensive fluctuations above a transition. We see it in low resolution X-ray scattering, but you don't see it in high resolution X-ray scattering. So I was going to show you that, but in the interest of time, I won't. And then I'll just finish with our conclusions, which are here. And that is that there are strong CDW fluctuations in cesium, vanadium, and antimonide that extend up to at least 1.7 times the 94 Kelvin transition to long-range order, and it's consistent with heat capacity. The CDW seems to coexist perfectly well. It doesn't go up, it doesn't go down. With superconductivity, at least at 2/3 of the superconducting transition temperature. And this might be even the elephant in the room, or something that's less expected and easy to understand, is that there seem to be these quasi-2-dimensional CDW fluctuations that are temperature independent, but they're present everywhere below 300 Kelvin. And so sorry for running over, and thanks for your time.
Let's all thank Bruce for this great talk. And we'll take some questions.
So what that means is that the CDW fluctuation you observe below 300 Kelvin, just above, let's say, 100 Kelvin, is something to do with this van der Waals bonding, or?
It's something to do with what, sorry?
So what kind of CDW fluctuation then you are?
Oh, so I mean, the only thing that we can really tell about the CDW fluctuations is their wave vector, right? So we know they correspond to a doubling of the unit cell in the Kagome plane, and in this case, it's a doubling of the unit cell in the along the stacking direction. But that that essentially never changes. We're pretty much we've done other measurements as well, but these measurements here, they're all at this 1.5 wave vector. So they all correspond to this doubling of the unit cell in the Kagome plane. And these two at the side here would correspond to a period 2 stacking. It could be the Star of David and the trihexagon or what have you, but it's a period 2 stacking along the C direction. So that would correspond to these two. But these other ones, the one that is at L equals 0, that's in phase actually. So if you like, and there's a large there's scattering everywhere. I kind of prefer to think of this as a streak of scattering or a rod of scattering, characteristic of a two-dimensional system. And it means that, because the features here, none of the features here are very sharp, it means that you sort of have all periodicities out to, a periodicity of infinity would be, that they just stack on top of each other, if you like.
Do you have any chance to look at the other compound, like a potassium?
No,
Okay.
no, we haven't yet.
I'm asking because, simply, when I look at the CDW, the trend is not consistent with my intuition, not like a potassium rubidium cesium, but this potassium rubidium cesium like that.
Mm-hmm.
So I has been thinking some kind of interlayer coupling is a bit.
Yeah, right, yeah. No, it would be, that's an obvious thing to do, is to do these same measurements on the other, on other samples, but we just haven't gotten there yet. Yeah. Thank you.
Hi, really nice talk. So my question would be regarding your heat capacity measurement.
Yep.
Did you try to analyze what is the entropy or integrate, or did you try to see the height of the superconducting peak? Because it seems small from here. I don't know if the numbers make sense.
Yes, so we didn't actually do the heat capacity part of the measurements. So that was, it's going to sound awful. It sounds like I'm blaming my coworkers, but so it was Walter Schnell and these three people basically that did the heat capacity measurements, and I think it was analyzed in those terms. But and it's not a secret what the answer is, but I don't know what the answer is. Yeah.
I see. Thank you. And did you try to, I don't know, because it's linear, and since it's an order parameter, you expect, like, if it's three-dimensional, two-dimensional, to have some.
Yeah. No, absolutely. Yeah. So this is a very odd order parameter, and because this is a scattered intensity, it should actually go like the order parameter squared. So if you're going to, this is a very bad thing to do, but if you're going to associate a critical exponent with it, it would be beta equals 1/2, which is a mean field critical exponent. But it's not a critical exponent because that's describing the full temperature dependence of the data, not just the temperature.
Yeah. Did you try to, I don't know, fit only the low temperature data after the CDW transition or something like that?
Right. So at low temperatures, actually, you don't see it very well here, but below about, no, you don't see it there at all, actually. If you just give me a second. Below about 20 Kelvin, there's no temperature dependence to it at all. So that's what was shown here. Or here, or here. Yeah. So so you can see, this is from 16 Kelvin down, and everything just fits on top. And so at temperatures of a few times TC, there's no temperature dependence at all, right? And with regard to you're correct to point out this very odd linear dependence, because most order parameters are curved, right? And so this eventually does come in flat at low temperatures, but you have to get to quite low temperatures compared to either, the 94 Kelvin CDW long-range order onset, or the 150 Kelvin onset where we see the fluctuations. But nonetheless, it's very odd to see a linear regime over that's that long. But what I was going to show you is that we've seen this before. So I ran out of time, but maybe I'll now cheat the chair and try to sneak in another slide. And actually, so these are also low resolution measurements done about 15 years ago on actually an insulating magnet, but a two-dimensional insulating magnet that has what's referred to as a spin Peierls phase transition. Anyway, so it's made up of these titanium moments, which at low temperatures, it's 3D1, so it's spin 1/2 degrees of freedom that couple antiferromagnetically and form these singlets. So it's like a valence bond state below about 65 Kelvin or so here. And then there's an intermediate state that is actually incommensurate. And actually all of this stuff here was seen in high-resolution X-ray scattering at almost the same time that we published this paper. But our measurements also showed this streak of commensurate fluctuations that actually goes up to, pretty much double the, it goes up to double the temperature at which you see the long-range order commensurate structure formed, okay? And actually, the kind of the interesting thing is that if you look at the temperature dependence of any one of these features individually, like if you look at the temperature dependence of this commensurate feature here, or these commensurate features here, or these incommensurate features here, each one of them individually has quite strong temperature dependence. But if you add them all up, if you just just imagine taking this and just adding everything up, you get this. You get this very straight line behavior over a very extended range. So actually, we have seen this before in two-dimensional systems, where if you add up all the fluctuations and the long-range order, you actually get something that looks very linear. So it's unusual, but actually it's not unheard of.
Thank you.
Yeah, thanks for a very nice talk. I actually had a question more related to the basic slides that you showed, just to understand the idea. So for the low energy, low resolution measurements that you're doing, you are essentially able to, the way we are looking at it is we are able to probe the fluctuation regime to 150 Kelvin. So where, as you mentioned, you expect more like a streak rather than the Bragg spots. So the first question was that, but you don't see anything at 94 Kelvin, right? Any discontinuous change in intensity?
Yeah, so we don't see anything special at 94 Kelvin, except in the measurement of the lattice parameter, right? So if I go back here, so while we're doing these measurements, every time we change the temperature, well, actually not every time, but often when we're changing the temperature, we remeasure the lattice parameter and recalibrate the measurement for the fact that the lattice is shifting a little bit. So as a matter of course, we're always remeasuring the lattice parameter, and this is the lattice parameter as a function of temperature. So usually this is not very interesting, but actually here you can see that there's a measurable jump as you get to 94 Kelvin. So that shows something at 94 Kelvin. But the actual measurements of the Bragg-like features that correspond to a doubling of the unit cell in the Kagome plane and a doubling perpendicular to the Kagome plane, that's these intensities here, and there's nothing special about 94 Kelvin there. That's right. In fact, that's the main conclusion.
Yeah. And the second question was that with the low resolution, you also have a larger spot size you're dealing with and low energy, and there's no less local heating, right?
Right.
Compared to the. Yeah. So how do I connect that to the fact that why wouldn't the high resolution be able to see any fluctuation regime?
In principle, they can. And actually, in fact, Stephen Wilson showed some results. It was not in this system, it was in the other one that had those trimers. I don't know if you remember exactly what he was saying, but they were seeing diffuse scattering. And so in principle, you can. But the high resolution measurement is, if you like, the volume of reciprocal space you're measuring for any one setting of the instrument is very small. I mean, that's what gives you the high resolution, right? Mm-hmm. And so that's great. If what you're trying to measure is a spot in reciprocal space, and you've got a very small circle, then you'll localize the spot and you'll measure its width and such. You'll do all sorts of things very, very well. Okay, but if you're trying to measure something that's very weak and diffuse, then what you're integrating in that small spot is very small, and so you'll confuse it with background. You won't notice that it's there, perhaps. It's not what comes naturally to a high resolution measurement. It's not that it can't be done, but it's not what comes naturally. Whereas it is what comes naturally to a low resolution measurement. Because if you've got a big integration in reciprocal space and you've got something that doesn't change very much, you're going to integrate a lot of it up.
Thank you.
And I'll be a bad chair, and I want to sneak a
Yeah.
a short question as well.
Sure, yep.
It might be just due to me being the least experienced guy in the room, probably, but you see that as this T-dependence goes down, it kind of saturates for a very high temperature range, and it's not like setting on zero.
Right.
So is it something that you expect? Do you expect it to go to zero, or if it's really is related to fluctuations, why would it be like temperature independent?
Yep. Good. Good question. So basically, so this plot here is coming from this data, and you can see that basically where this goes to zero, that's where the peak goes away. So the intensity at that point does not go away, and that's because you're sitting on this streak of scattering, which is it's at the half-half positions within the Kagome plane, and but if you go perpendicular to the Kagome plane, you've got basically a rod of scattering, which is temperature independent. And so when this scattering does go away, it's still sitting on that streak of scattering. So you're not actually at background. Yeah, that's correct. Yeah, and so this other piece here, right, which is most of the scattering actually, is there. It's there at 300 Kelvin, right? It's God knows where it goes away, if it goes. Well, I'm assuming if we melted it, it would go away.
That's all. Thanks.